And so we can measure the enthalpy of activation for the uncatalyzed reaction and compare that to the enthalpy of activation for the catalyzed reaction to see if we see a reduction in the enthalpy of activation in the presence of the catalyst. Okay, and so that's what they've done here. And how do you measure then the enthalpy of activation? Well, you use the Arrhenius equation. And what the Arrhenius equation actually gives us is not the enthalpy of activation, but something very closely related to it called just the activation energy, E sub A. And so if you measure the rate constant of a reaction at many different temperatures, you can get from that the activation energy. And so generally what you do is you transform this equation just by taking the log of each side of this equation, and now it transforms to this. And so then if you plot the log of the rate constant versus 1 over the temperature, the slope of that line will be equal to E sub A over R, right? The intercept will be the logarithm of A, but we don't care about the intercept, right? So we know R, we know the slope of the line, and therefore we can calculate E sub A. Okay, so E sub A then is proportional to the slope of the line, right? And so what did these scientists, Sievers et al., do? What they did was they measured the rate of the ribosome catalyzed peptide bond formation using this reaction here, which we've already talked about. Okay. And so they basically measured the rate of this reaction at a variety of temperatures. Okay. And they generated this then Arrhenius plot where they're plotting the log of the rate constant versus 1 over the temperature. 1 over the temperature times 1,000, just so they have nice numbers here. Okay. And then they also measured the rate of a model reaction, which they considered a model reaction for uncatalyzed peptide bond formation. So this is the reaction that they considered to be a model for uncatalyzed peptide bond formation. They measured that at multiple temperatures, and they generated an Arrhenius plot. And they saw that catalyzed peptide bond formation is much faster by 7 orders of magnitude at any given temperature than uncatalyzed peptide bond formation. But surprisingly, what they saw is that the slopes of these two lines are what? They're almost the same as one another. These two lines are parallel to one another, right? So they have the same slope. Okay. And since the activation energy is just a function of the slope, what that tells us is that the catalyzed and uncatalyzed reactions have the same activation energy. So that seems to argue against chemical catalysis. Okay, well, actually, let me explain that a little bit more clearly. Okay, so the only thing you have to worry about on this slide are these two equations, right? So far we've been talking about the activation energy. I told you that the activation energy is very closely related to the activation enthalpy. It's actually related by this equation. So the activation energy and the activation enthalpy are almost the same as one another. There's this small correction factor, MRT, where M is the reaction order. In other words, it's the number of reactants. Okay, so the fact that the activation energy doesn't change tells us that the activation enthalpy doesn't change. Okay, so how are we accelerating the reaction? Well, if we're not changing the activation enthalpy, we must be changing the activation entropy, right? And so here's the equation that you already know that relates free energy, enthalpy, and entropy. So the free energy of activation, delta G double dagger, is equal to the enthalpy of activation minus the temperature times the entropy of activation. Okay? And so what Sievers et al. Did then was actually to measure the free energy of activation. Having already basically determined the enthalpy of activation, what they did was to measure the free energy of activation, plug the free energy and the enthalpy into this equation to solve for the entropy of activation. Okay. Okay, and you don't have to worry about how they determine the free energy of activation. If you want to know, they basically use this equation here. They measured the rate constant. Well, they already had measured the rate constant as a function of temperature, and then from this equation you can get the free energy of activation. Okay, and then knowing the free energy of activation and then the enthalpy of activation, they can solve for the entropy of activation.